Welcome to APEC. It's May 14th, and I'm your moderator, Tim Ventura. First, I'd like to thank everyone for joining us on this call, along with everyone watching us on YouTube. In today's session, Rob Chambers will discuss the local origin of inertia in the Reed EM Propulsion Drive. Jarod Yates will present on warp drives in the TR-3B, and we'll be playing the Miguel Alcubierre interview. Mark Sokol and Jeremy Rys are going to be joining us live from MUFON, and we'll be finishing off the event with an open discussion and some ad hoc presentations by conference attendees. So again, just the normal quick reminders, you can view our conference replays, details, and speaker info on our website at altpropulsion.com. You could save those questions for the Q&A session after each presentation. Please raise your hand in Zoom using Option Y on Mac or Alt Y on Windows. You can also type your questions into chat and we will go through them after each presenter finishes. So I am honored and very pleased to introduce you to our first guest. Rob Chambers is joining us to discuss Roger Jennison's model of the electron as an electromagnetic wave trapped in a phase-locked cavity, which suggests a local origin for inertia in fundamental particles. He's also going to explore Larry Reed's work with the model as a starting point for a potential means of propulsion through the manipulation of the Broglie matter waves within cavity resonators. He is finally going to present a speculative craft design combining this type of propulsion with shielding using negative index metamaterials. So everyone, let's welcome Rob to today's event, and I will hand things over to him to get started. Wonderful. There we go. And Rob, I'm asking you to unmute now, and I'm going to admit all. Okay.
Okay.
Perfect.
I think we're there now. Okay.
And hopefully the spotlight, I did a replace spotlight, so it should be completely focused on you.
Right. Okay. Are you seeing my my presentation?
I am. There we go. Okay. Perfect.
Right. Okay. So I'll let you know when it changes to the first, well, to the second slide, so we'll know if it's working. Right. So yeah, as Tim pointed out earlier, it's none of this is actually my own work. I just wanted to bring this to people's attention. I think that it's something which possibly a lot of people don't really know much about or have heard of in the past. So yeah, so I shall start. So let's see. Okay. So are you seeing the second slide?
Yeah, it looks great.
Good. Okay. Right, yeah. So essentially, this is a kind of a story of two people. The first one is well, actually one of my professors at university, Roger Jennison, who's quite eccentric kind of guy, but very knowledgeable and very well respected. In fact, the electronics lab at the university is now named after him, as he died about 15 years ago. After being a student, I had no idea, in fact, that he had been involved with what became Project Green Glow, the initial roundtable between BAE and several universities about gravity research in 1990. I mentioned him in passing in my last presentation, and I'll fill in a little bit more now because I've learned a few more things about him than I knew at the time. He was a noted radio astronomer who worked at Jodrell Bank, which, if you know, is a very famous radio astronomy site in the UK, one of the earliest with a large directed dish. And he was there in the very early days of the 1950s, and then moved on to universities afterwards. And he developed several radio interferometry techniques known as the closure phase and self-calibration in very long baseline interferometers, which are used to this day. And the photo here is actually from an interview he gave to, again, an American audience may be aware of Arthur C. Clarke's Mysterious World. It was a TV series in the early 80s. Which is British. And I would show the clip, but I know we've had problems in the past with showing TV clips. So I will provide a link to it, however. So just want to make sure I've covered everything. Yeah, yeah. Yeah. So what are we? I suppose the most interesting part of his work to our group is when he did a number of papers concerning inertia, in particular starting with the electron, but it's something which you can apply to any fundamental particle and by extension, any mass, any matter. He showed through this series of papers, and also where I've quoted here is a magazine article which summarized all of his papers, all the work he did. And it was a publicly available newsstand publication for amateur radio enthusiasts, and you can download it nowadays as well. And it seems that not many people really realize the significance of it. Those of you who follow Mike McCulloch's blog, a few years ago someone sent him a copy, and it blew his mind. And it has a similar effect on a few people. So in essence, then he showed that it's probably better if I kind of describe kind of a summary of the article. When initially they were looking at, because his special field of interest is accelerated reference frames, and he was concerned with, well, how do we measure things in an accelerated reference frame? And through, I don't know exactly the ideas that were exchanged, but in essence, he decided that the best way to do this would actually be to use an electromagnetic wave, if you could somehow capture it or trap it or limit it in some way. And when he thought about this, and he realized that if you could somehow trap a wave in this way, that it would exhibit the properties that we associate with inertia, that if you pushed it with an external force, it would accelerate, and if you remove the force, it would carry on moving until it was stopped. And he did some more work on this. He was able to show that a trapped standing wave effectively had rest mass, and it possessed inertia. So he made the point also that electrons look much like photons that are locked in a kind of a self-made trap. So that, for example, when an electron and positron collide, they annihilate cleanly and you get two oppositely polarized photons. And also, if you fire photons of slowly decreasing wavelength at each other with a heavy nucleus nearby, you will, at a certain point, certain wavelength, you will trigger the creation of a positron and electron, pair production. And so he thought, well, this looks like electrons and photons have a very close association. And he postulated a tentative model of the electron, which has two orthogonal spinning electromagnetic waves in phase quadrature, which are phase locked at the Compton wavelength into a closed loop system. Now, he doesn't know and didn't know why it was at this Compton wavelength, but if you assumed that that was possible, then you could actually predict a lot of the properties of the electron, which until that time, you had to kind of just take as read, that there was no real explanation for why the electron had charge or why it behaved the way it behaved. Just also as a note here that although he was the head of department and very well respected and so on, he was also very interested in things like dowsing and ball lightning. I think with ball lightning there was he probably considered that as being a kind of a macroscopic version of what he saw with the electron. So that was of particular interest. And in fact, he also wrote a letter in Nature magazine and was interviewed by Arthur C. Clarke's Mysterious World on the fact that he witnessed ball lightning in a plane in 1963. I think he was flying down the East Coast, I think Washington to New York, something like that, in the middle of a thunderstorm, and the plane was entirely metal frame, as they were at the time anyway. And he noticed this ball of light about a foot across that flew from the pilot's compartment to the back of the plane at about walking pace and at about an arm's length from his face. And so he was able to document this with the kind of the eye of the physicist. And yeah, so I say he's published on this several times, and the interview is very entertaining. Yeah. Which you'll see why if you look at the interview. I'll put these links in the chat afterwards as well. Yeah, so in fact, I've stolen this diagram from Mike McCulloch himself, so apologies to Mike. So to return to his idea of an electron model, what he has here are two oppositely charged plates with a wave, electromagnetic wave between them, which is effectively pushing the plates apart. And effectively, then you've now trapped a photon. We're not going to delve into how you get it into that position, but this is how, if we assume this layout, you see that the wave bounces around inside, and it pushes the cavity plates outwards. And so you essentially create a stable system by doing this, by creating opposing charges and opposing pushes. But if you then push the cavity, in this case from the left, externally, the wave that's just bouncing off the left wall, the light blue wave, is given more energy by the wall pushing it, and the now super energetic wave pushes the right wall so that moves as well. However, then the photon bounces back, the dark blue wave. It then has lost energy, so it has less energy when it gets back to the left-hand wall, and so that wall is effectively pulled rightwards. So if you take away that initial push, then the process continues so that the cavity continues to move rightwards, and essentially you have inertia, that the cavity will then keep going at that speed unless you push it in some other way. Now, as Jennison remarked, the only other suggestion really that could explain inertia was Mach's principle, which is only a qualitative hypothesis really, and it doesn't account for the kind of precise observations of inertial mass, inertial force that we can do. So this model appears to reconcile many of the differences between the classical and quantum behavior of matter. A phase-locked cavity has a transfer function which reproduces the quantized relationship between an external influence and an elementary mass. In particular, if you accept that there is a unique wavelength, this Compton wavelength, at which electromagnetic waves can lock into a closed loop system, then a particle can be formed which has all the properties of an electron, or the following properties, I should say: inertia, a quantized transfer function, rest mass, angular momentum, which is half classical angular momentum, an electric field equivalent to a localized charge, and magnetic moment, including the anomaly that's associated with the electron, and also preserves the proper units of length and time when it's accelerated into a different frame. And you also have indeterminacy, as you'd expect from Schrödinger and all the rest, arising from lack of knowledge of the phase of the internal waves. So at the moment then, we only need one postulate for this model, so that at the annihilation wavelength, when you create or destroy a positron and electron, where are we? Yeah. So at the annihilation wavelength, you can lock this in a perfect equilibrium. This one postulate then can dispense with all the separate postulates that have been required for other descriptions of the electron. And you can also derive Newton's second law and E equals mc squared from this model in an entirely classical way without having to use any quantum calculations at all. The only time that the quantum effect would show up here is if your force is removed before the photon has the chance to return to its original position. So if you push on the left-hand side here, but then immediately remove the force, you will create what's called Compton scattering, where you, instead of the electron simply moving along, it loses, or it shoots off in a direction which is not predicted by classical physics. But assuming you maintain the force long enough, you essentially can treat this as an entirely classical system. And yeah, the only real drawback to this model is that we don't know why it's constrained at this wavelength. I think well, we'll discuss later on, but this is Larry Reed, has done some work on the electron as well, where he has come up with a more geometrical explanation for why that is. But that's not particularly relevant to my talk, so I'll leave that to the interested reader. So now Jennison also built macroscopic analogs of this idea. He used a version with lasers and a version with radio waves, and this is what is shown here. So we have a distance L between two trolleys that are, you'll see that there's servo motors which assist the movement. So because they're so large and because the wave and the force of the wave in between is so small, they have to be magnified artificially. So it's cheating slightly, but the principle is the same. So here the distance L between them is maintained constant by independent sensing and control on each trolley. And this effectively amplifies the very weak control that's exerted by the boundary conditions of the wave, although the speed of response is degraded, so it jitters slightly. It's not a perfect model. Yeah, the independent trolleys, they accelerate and move as though they're a single solid body when you apply a horizontal force on one trolley only. And when you remove the force, the system coasts along at the terminal velocity, maintaining that distance L constant throughout. So this kind of demonstrates that although he started with an electron, you can extend this into the macroscopic realm. There's no reason why the same principle can't apply to larger objects. So, and he also did many other experiments which were quite interesting in the way that they were able to use simple materials, simple ideas to do some quite interesting things. And in this case, what I've illustrated is a way that he was able to actually effectively stop and even reverse the direction of an electromagnetic wave in the lab. What he has here is a set of delay lines. So he's already slowing down the wave in the clockwise direction, and then rotating the entire thing in the counterclockwise direction. And with these little circles around the edge represent LEDs. So he had red and green LEDs to indicate where the peaks and troughs of the wave were, so that you have visual indication of when the wave was actually static. So it wasn't a strobing effect, it was literally the wave was stopped and the lights would show you exactly where it had stopped, obviously in the lab's own frame of reference. Now, what he found was that effectively you get a static electric charge out of this. So although I think later analysis showed that it wasn't exactly as simple as that, but it's a very interesting experiment, and it showed what you can achieve with quite a small budget with the right kind of ideas. And this is also reflected in, this is an experiment which was suggested at the BA University Roundtable, which preceded Green Glow. I mentioned this last year, so I'm just going to just briefly explain this one. This has never been performed to my knowledge, but again, it seems like a relatively simple experiment which could show a link between big G, the gravitational constant, and electromagnetic wave characteristics like the speed of light. So in this case, you have a long tube with capacitors at each end, and by rotating it, you vary their height relative to each other in the Earth's gravitational field. And if you have a sensitive enough capacitance bridge, you can, if there is one, detect a change or difference between the electrical permittivity of each capacitor. And if you can show that, obviously you would want to try it in different orientations as well to make sure that there were no experimental errors involved. But in theory, then there's a way in which you could demonstrate a direct link between gravity and electromagnetism using this kind of apparatus. But as I say, as far as I know, it's never actually been done. So, yeah, this is moving on to the second part of the presentation. Larry Reed has extensively referenced Jennison's work in his own work. As far as we know, he's a retired aerospace engineer in Torrance, California. He has written a book which is available through the usual outlets called Quantum Wave Mechanics, which has separate chapters, large chapters on light, electricity, and gravity. Most of his papers and presentations are online, easily available. And in fact, the book itself, most of the book is also online. And most of what I'm about to present is actually an extract from his own presentations. So in fact, it's very much a subset of his presentation because he goes quite a lot further, and I'm leaving out a lot of the more complicated mathematics, and just in order to appeal to a wider audience. If you are interested, obviously his papers and books are easy to find, and I'll put some links in the chat as well after that. So we've actually also, I think Tim has already asked Larry to appear on APEC, but he doesn't want to. So I'm hoping to do his work justice. Obviously, I'm sure if he wants to appear after this and and correct me or anything else, I'm sure Tim would welcome his appearance. So, right, I'll just move on. Okay. Yeah, so just as kind of a resume of, and to relate this back to Jennison's work, we start from a signal generator, normal traveling wave, which you can imagine you could then trap inside a resonator of some kind of hollow tube or cube of some kind. And when it's at rest, you just have a standing wave because it's just reflecting off the end and bouncing back and forth. And then what he's saying is if you were then to put it into motion, you disrupt the pattern. So you still have a kind of a standing wave, but it's now kind of moving and it has a more complicated waveform. And he associates this waveform with the de Broglie matter wave. So he's saying this is essentially a kind of a macroscopic version of the de Broglie matter wave. And so I'm covering everything I wanted to cover. Right. Yeah, so you can imagine this is a freely propagating photon in a zero curvature vacuum, which has zero rest mass. And you trap it between two Bragg mirrors in a phase-locked cavity resonator, and it acquires effectively, it acquires rest mass. And a light beam, when it reflects from a mirror, you get momentum reversal, which cancels the momentum of the incident wave. And he's saying that the resonator mass motion, it represents a disequilibrium or a dissonant state. If we think in terms of harmonics, you have a consonant and a dissonant state, and this dissonant state is this more complicated wave in the third level. So this is not a terribly clear diagram. It's trying to illustrate the behavior when you apply an external force. And at the first stage, you're at t equals 0, t0. And you're applying the initial push from the left. You're creating a blue shifted wave, which then hits the right-hand side. In the middle, you have the situation at t0 plus delta t, where delta t is the length of time it takes to go from left to right. So you're kind of at an intermediate stage. So you're saying, okay, you're sending a blue shifted wave to the right, a red shifted wave to the left, and they build into or create a contracted moving standing wave packet, as he has here. And so you can associate the various, the modulation envelope wavelength and the speed and so on that you should get given the initial force that you use. So what he's saying here is that the motion of a confined closed loop electromagnetic wave exhibits inertial characteristics due to what he calls self-referral dynamics. So this is the back and forth interference. So when you apply an external force, the blue shifted incident wave exerts an excess radiation pressure on the reflecting wall on the right-hand side, and the red shifted reflected wave exerts a decreased radiation pressure on the motive wall, the left-hand side. And once set in motion, the wave system remains in motion until you are acted upon by an external force. And the de Broglie wavelength represents a matter wave generated by the motion of matter. So as shown, the wave medium corresponds to an ordinary positive index of refraction. So you get a phase velocity propagating in the same direction as the group velocity. And for a negative index of refraction, metamaterial, the phase velocity propagates in the direction opposite the group velocity. So you have what's called anomalous dispersion. And for a non-dispersive medium, so this is where there's zero refractive index, the phase velocity equals the group velocity, and the Bragg mirrors approximate perfectly reflecting conducting surfaces and don't reflect all frequencies. So you're eliminating any other frequencies. And so what he's saying from this is that matter, or fermions in particular, consist of stored electromagnetic energy within resonance structures like electrons, protons, atoms. And this self-referral dynamics of stored electromagnetic radiation within a cavity resonator in motion creates de Broglie matter waves, or at least the macroscopic equivalent. And once set in motion by an external force, it continues in motion in accordance with Newton's second law. And nodal displacement due to phase and or frequency discordance results in resonator mass motion. The thrust is proportional to the internal radiation pressure imbalance. So obviously, the more you imbalance, the more you push, the faster it should go. And just to clarify that, then in this case, what we're using here, we have a single signal generator. We're going to use this to try to move the cavity resonator. And what are you saying here? This obviously has similarities to the Roger Scheuer EM drive and also Canet drive and a few others. And what he's saying is that a major stumbling block in the demonstrations of these kinds of reactionless microwave drives to date is you get extremely low thrust because because of the single frequency magnetron excitation of a few gigahertz. The resonator walls, which are free to move, tend to settle in at the node points. And with a single frequency excitation and its associated harmonics, oppositely directed nodal displacement occurs only when changing frequency modes. And standing waves stay put with the end nodes at the boundary walls. And the resonator will then just kind of jitter in place with no dissonance or net motion. Motion involves alternating jumps between consonant and dissonant ratios. I was also thinking on this also with what Roger Scheuer has said about his drive, is that it actually requires a load in order to work. So that did make me think that maybe he is onto something here, because for the Scheuer drive, you have to have something to push against, so that it's not simply down to the presence of a single signal. So this made me think maybe there's something to this. And yeah, in fact, Larry Reed has also said that non-uniform field effects that are associated with asymmetric frustochronicle resonators are minimal due to the very modest electromagnetic field intensity gradients and the nonlinear polarization effects that are developed for the given low energy input conditions. So I think he's also saying that the amount of energy you're using is also important. So what he's proposing is to use, in essence, to use a resonator at each end, a signal generator at each end, and one which provides a blue shifted version of the wave, and one in this case on the right, which produces a synthetic red shifted wave. And with these two resonators, with two generators, you can produce whatever kind of moving standing wave or de Broglie wave you want. So what we're essentially saying here is, instead of using an external force, we're going to mimic the effect of an external force artificially by internal manipulation of electromagnetic waves. What he's saying here then is that mass transport is affected by varying the phase and or the frequency difference of the two counter-propagating waves. So you get a moving standing wave. And this is the inverse of what the naturally occurring Lorentz Doppler effect associated with motion. He refers in his work to what he calls the Lorentz Doppler effect, which I assume, from what I can tell, is effectively a relativistic Doppler effect. So it's a Doppler effect taking into account special relativity. And what he's saying here is that we should be able potentially to create an inverse version of this in the same way that we have inverse Doppler effect, inverse Sagnac effect, inverse Faraday effect, inverse Compton effect. So there are many, many cases in physics where an inverse of an effect exists. I know most famously, I think what we discussed in my last presentation was you have the inverse Barnett effect. So you have, which is also called the Einstein-de Haas effect. And so he's saying that if these effects have an inverse in nature, then in theory, we should be able to produce that inverse effect ourselves as well. And essentially, this is what the rest of the presentation relies on. If this isn't true, if this isn't a valid idea, concept, then none of the rest of it really makes sense. So we are proceeding on the assumption that we can induce an inverse effect to the Doppler effect. And so what he's then saying is that a single standing wave is sufficient for limited applications where the velocity is much less than the speed of sound. However, an internal wave system lacks the means to affect uniform acceleration of the surrounding medium to minimize dissipative energy losses in observables. So to minimize things like drag, noise, shock waves, a localized zone, which is external to the resonator, on the order of the length of the resonator, it needs to be kind of managed or provided for. And also there's no way to avoid excessive stress or strain on the resonator when acceleration or deceleration is applied over too short of an interval. So if you're colliding with something, you would have a sudden jerk, which obviously would damage, unless managed, it would damage your system. So to avoid excessive jerk, you have to ensure uniform acceleration of the resonator and its surrounding medium to avoid the effects of strain, essentially, on the vehicle, on the device. So you need to generate these matter waves internally and externally with gentle changes of the frequency ramp rate. And so what he's suggesting here is to use 3 or more signal generators, which are overlapping they're creating a phased, overlapping, multi-band, swept frequency wave system or harmonic in what's called a Shepard-Rissett glissando sequence. And the forcing function inputs include phase and frequency difference, offset interval, a sweep period, and ramp rates that precisely control the acceleration. And up chirp provides acceleration and down chirp provides deceleration. Now, a Shepard tone, which is named after a guy called Roger Shepard, in audio terms, it's a sound that consists of a superposition of sine waves that are separated by octaves. And when you play it with the bass pitch of the tone moving upward and downward, it's referred to as a Shepard scale. And this creates an auditory illusion of a tone that seems to continually ascend or descend in pitch, yet it ultimately gets no higher or lower. And a guy called Jean-Claude Rissett, he subsequently created a version of the scale where the tones glide continuously, and it's appropriately called the continuous Rissett scale or the Shepard-Rissett glissando. And when it's done correctly, the tone appears to rise or fall continuously in pitch, but it returns to its starting note. And this is used in sound effects in films and things like that. In fact, I have an audio clip which I think play. It's from Wikipedia, and so there should be no licensing issues. I can read out the necessary information here. It's from Wikipedia. User is called Varenk, and it's created under the Creative Commons Attribution Share Alike 4 international license. And if you contact me via Tim, I can provide you with a copy of it. It's one of the terms of the license. So I will try to play it. I'm not sure if it will let me. It might be a little bit loud and ear-splitting, so I apologize in advance.
Oh, Rob, I'm not hearing anything.
Oh,
You,
okay.
you know what, when you do the screen share, it makes you check share audio separately. That might have been the issue.
Yeah, okay. It's not important. It's just yeah. If anyone's interested, I can send them the link.
Oh,
It's on
okay.
the.
I'm sorry about that. Yeah, I
Yeah,
run into that as well. Yeah, it makes you check a share audio box completely
yeah,
separately. So
yeah, yeah. I mean, yeah, you can look it up on the Wikipedia page. It's on there anyway. So I've, in fact, it's I extracted it as an MP3, but the original it sounds exactly the same. It's essentially what it's saying is everything is separated by an octave, and you have this continuous change, but it actually the tone never really changes. It's just a way of controlling, of applying finer control over the system. So it's really just a suggestion. It's not necessarily how it has to be done. So yeah, so in this case, if you have say 3 signal generators, you can create a barrage of wavefronts that will increase radiation pressure and therefore the thrust. If you reduce the local velocity of light in a negative index metamaterial, then this may give you an inverse Doppler effect, and alteration of antenna radiation impedance and space-time impedance and de Broglie matter waves. So just set it off again. Right, okay. So yeah, this is kind of to return to an earlier diagram. This is how Larry Reed proposes to essentially perform this function of artificially creating waves of the right frequencies and to modulate them. So, so this is a conceptual diagram for the induced motion of a phase-locked resonator with a phase conjugate reflector, which is irradiated by amplified Lorentz Doppler shifted pump beams, which modulate a standing wave, which then generates a ponderomotive force. A simulated Lorentz Doppler effect results in a contracted moving standing wave, which is what you see in the third level there. Pump beam energy input provides the kinetic energy of motion. So it's not getting energy from nowhere. It's not we're providing it with energy, and then we're manipulating that in a certain way that mimics an external force. So we're creating a kind of internal force. So yeah, just to summarize then, this is Larry Reed's own table, which he is saying these are the characteristics that you should see from this kind of matter wave propulsion. As you can see, the kind of characteristics he's talking about are the kind of things that we nowadays associate with UAP, UFO, and various sightings. So you can see that he's clearly associating his ideas with. He's suggesting here that that is possibly how the propulsion is performed in UAPs. So yeah, so this is a kind of a messy diagram we have. It was hard to kind of simplify this. So what he's illustrating here, mainly I'm concentrating on the right-hand side, is he's trying to explain how what's called four-way mixing is used to create a mirror, a phase conjugate mirror in this case. And coming in from the top left and bottom right, you have pump beams, which provide the power. And effectively, well, it's probably easier if I use his explanation, that the reflecting boundaries of a resonator cavity need not be limited to conventional mirrored surfaces. The reflectors can take many forms, like magnetic mirrors, retroreflectors, phase conjugate mirrors, and so on. In a conventional mirror, a reflected electromagnetic spherical divergent wave from a point source remains divergent, so it just spreads as it reflects. If the wave is reflected from a phase conjugate mirror, the wavefront is inverted in a convergent beam back to the source in a time-reversed replica. Phase conjugate wave generation can be accomplished by 3- or 4-way mixing in photorefractive crystals, in nonlinear optical Kerr media, or metamaterials. 4-wave mixing is a nonlinear effect arising from a third-order optical nonlinearity described by a susceptibility coefficient in a Taylor series expansion, resulting in induced polarization of electric field strength. So in other words, you're feeding, in this case, 3 beams into to create an effective reflective surface, virtual surface for another beam, which you can then modulate the frequency of. And nonlinear phenomena that produce phase conjugation include Brillouin scattering, Raman scattering, Kerr full-wave mixing, resonant full-wave mixing, photon echoes, that kind of thing. A Bragg reflector is formed from an interference pattern in the overlap zone of two counter-propagating beams. So this is what we're describing on the right-hand side here. The effect is similar to conventional Bragg X-ray diffraction from crystals, where atomic lattices form periodic scattering centers. A signal beam that's incident on the interference pattern results in a reflected phase conjugate wave propagating back along the path of the signal beam. And this is a diagram here which illustrates the phase conjugation full-wave mixing process for a case where the pump beam frequencies are not the same. So you're able to manage the frequency of the wave that comes out. Now, so this table or set of diagrams really summarizes the behavior of phase conjugate mirrors. So using pump beams of different frequencies, you can engineer things such that you can downshift frequencies. So you can go from a normal beam to a redshifted beam, or from a blue shift to a red shift. So overall the downshift, or zero frequency shift, or a frequency upshift by managing your pump beam frequencies. So this shows all the various possibilities. And as a kind of a full-up system, I'm not sure how clear this diagram is, but essentially what he's got is, you recognize the central de Broglie matter wave being reflected to and fro, up and down in the middle, and two sets of three transmitters of producing pump beams of different frequencies, which supply the energy and the frequencies, the necessary frequencies to manage the matter wave in such a way that you create, in theory, synthetic thrust. So you now have your system, I guess, in say that, yeah. So just to kind of illustrate this, it's the high internal radiation pressure, which is provided by high frequency standing wave modulation over a wide frequency range. You have amplified, synthesized Lorentz-Doppler shifted pump beams, which modulate a standing wave in a phase conjugate resonator to generate a matter wave, which induces motion of the wave system. And then the energy of motion then is proportional to the number of frequency pairs. The frequency sweep rate is proportional to the frequency difference in sweep period interval. The wave system motion is in the direction of the frequency gradient. The starting and ending frequency sweep rates may be adjusted as desired to decrease the onset of acceleration and deceleration. So that reduces inertial stresses and strains. And this is akin to gently curved freeway on or off ramp. So you can ramp up and ramp down gently. And so you have your device, in theory, your propulsion system, but you also need to protect it if you're going to house it in something which is going to travel. And also if you have occupants, you have other delicate machinery or electronics, you need to look into how you're going to protect that from the sort of hostile environment that you're going to produce or going to be present in. And what he suggests, this is Larry Reed's own diagram, and he's suggesting that you employ what's called a whispering gallery mode resonator. So this is where, well, historically sound, but also any kind of wave can be kind of trained to go in around a suitably curved area. Now, he's also saying this is something which can be done with negative index metamaterials to redirect either, well, in the bottom left, he talks about the gravitomagnetic permeability. So that would assume a negative, a metamaterial which also has a high gravitomagnetic permeability, which may or may not be possible. This is, I suppose, speculative at this point. But on the upper right is, I suppose, more of interest in that this is more about redirecting electromagnetic energy, and again employing what we call the inverse Lorentz-Doppler effect, that waves could be routed around a sensitive area whether it's within a craft or in space. So yeah. So yeah, in fact, on the right-hand side, what we have is a geometrical model of an EM cloaking field in which energy flow is directed around an object. A positive mass object is enveloped in a medium of negative refractive index, deflecting the incident radiation away from the central mass. So it's the opposite of an Einstein ring that you see with often with black holes and so forth. So a negative index emitter material can serve to induce an analogous electromagnetic flux distortion effect to so I think you can probably clearly see what he's going for here. In Larry Reed's work, he often shows how his ideas can be incorporated into well-known shapes and objects. In his book, there are many examples of the classic flying saucer, where he's used that as a base to show how his propulsion ideas could be incorporated in something. And in this case, this is obviously his take on the Tic Tac. So what we see here is that you are protecting your system, your propulsion system, using a metamaterial and as a resonator. And this is what he calls the whispering gallery mode oscillator, and carrying evanescent waves. These are extremely near field electromagnetic waves, as a way of, again, managing or generating the de Broglie matter waves around the outside to help to protect the craft or the device. And so just to summarize here, he's saying that increasing the magnetic permeability of a negative index metamaterial, it will reduce the local velocity of light and results in an inverse Lorentz Doppler effect. So this is the reason for the enclosure being a metamaterial. And so this metamaterial external whispering gallery resonator encloses an internal phase conjugate matter wave resonator, as we've seen in previous slides. And it may conceivably be used to generate broadband evanescent near field matter waves with inverse Lorentz Doppler effect, which will accelerate the surrounding medium. And the inverse Doppler effect results in an energy flow which is opposite to the direction of the resonator motion. And kinetic energy is imparted to the surrounding matter by the artificially generated de Broglie matter waves. And it augments the ponderomotive thrust induced by the internal phase conjugate resonator, which imparts motion to the resonator assembly. In each case, the kinetic energy of motion is provided by the amplified Lorentz Doppler pump beams, which modulate the signal, and phase conjugate beams, creating synthesized de Broglie matter waves. So he's just kind of reinforcing the point here that by choosing, by the selection of an appropriate medium for your generators, for your creating matter waves, that you can manage the direction that they travel, the direction of force and thrust that you get out of each one. Right, now the next slide, I wasn't in my original presentation, but after hearing what the next presentation is, I thought this might be quite fun. As I said, Larry Reed is quite keen to put his devices into classic shapes. So in here we have the classic triangular, or TR3B, I guess, where he's inserted his own propulsion methods. So at the three corners, he's essentially repackaged essentially the core means of propulsion into a sphere. And in the center, he has some kind of attractor or repulsor beam based on the same kind of principles, but I'm a little bit dubious about that. It seems to require a Bragg interference grating at the focus in order to actually work. So I'm not sure it's really very practical. But certainly the propulsion at the three corners is something which Larry enjoys doing. He's either doing it as a classic flying saucer, or a Tic Tac, or a flying triangle. So I thought you might enjoy that. So yeah, so for me that's the end, and thank you very much for listening.
Rob, that's amazing. That is amazing. Wow, and like seriously in depth. Okay, let me do this. I want to remove the spotlight. I am going to, let me see, I'm going to stop your sharing there.
Yeah.
Okay. And I want to put the very first thing, I want to put this thing on gallery view. Everyone, please give an enormous hand for Mr. Rob Chambers.
Thanks.
Rob, that was absolutely tremendous. You just kept drilling down. I was like, oh God, this thing is technical. So
Yeah, I tried to make it less technical.
no, it's wonderful though. It's absolutely wonderful.